Okay, so our final set of lectures this week will be by David Kutasov from the University of Chicago, and he'll tell us about branes and gauge theory.
Okay, good afternoon. I indeed would like to discuss some issues regarding the dynamics of branes in string theory and how it corresponds to interesting gauge theory phenomena. But of course, it's going to be a very, very small subset of the things that one can say on the subject. So I will spend the first few minutes talking about the motivations for the specific things that I will discuss here, which also will help to orient us regarding where we're going with all this. So, of course, eventually what we would like to do is use string theory to say something about the standard model. And there are two places in the standard model where the picture that we have currently is not complete, and we would like to understand better what's going on. One of those places is QCD, which you've heard about in, say, the previous lecture. And there, things are complicated because, well, first of all, as you know, QCD is an SU3 gauge theory with some flavors of quarks in the fundamental representation. And this theory becomes actually manageable at high energies of the order of 1 or 2 GeV. But most of the interesting phenomena in this theory are happening at energies that are a little bit lower than that. And at those energy scales, this theory is very hard to control. But over the years, people realized that it has a few qualitative features that are of a lot of interest. One is confinement of quarks. Quarks are supposed to be confined inside hadrons and not appear as asymptotic states in the S matrix. A second one is the breaking of a certain chiral symmetry. So if the quarks were all massless, which is actually a good approximation for the first two flavors, for the U and D quarks, there would be an SU and F symmetry rotating the left-handed quarks and a separate SU and F symmetry rotating the right-handed ones. And again, in nature, this is a good symmetry with NF equals to 2, the U and D quarks. And this is a symmetry, an exact symmetry of the Lagrangian when the quarks are massless. But in fact, it's broken by the dynamics, even in this limit, to the diagonal SU and F. And this has to do with a lot of important physics having to do with pions, etc. And the third thing that is observed experimentally and we would like to understand better is the phenomenon of Regge trajectories. If you actually look at the spectrum of states, or more precisely, the spectrum of resonances in actual accelerator experiments, then you will see that they lie on asymptotically linear lines like this, which are called Regge trajectories. Asymptotically, the mass squared is linear in the angular momentum. And there are lots and lots of particles or resonances on these lines, hundreds of them, before, of course, all of this terminates somewhere around, let's say, 2 GeV, depending on which precise particles one is talking about. And all these things are known to some using a combination of experiment and all sorts of other techniques. But it's not really understood from any kind of first principle point of view, and we would like to do better. So the direction that we will follow actually originates many, many years ago, and that is to generalize from SU3 to SUNC and take the number of colors to infinity. And there are reasons to believe that the theory in this limit has all these features just like real QCD does. In other words, it does confine quarks. It breaks chiral symmetry if the number of flavors, let's say, is kept fixed in the limit where the number of colors goes to infinity. And these resonances that lie on Regge trajectories become more and more narrow as the number of colors grows. So all these things were realized very early on in the discussion of this large N limit, and therefore people believed or still believe that the large NC theory is somehow very close to the physical one, and the original thought was that we will solve analytically the large NC theory and then include 1/NC corrections and shed light on the physical QCD. This turned out to be hard, so the large NC theory is hard still. And we will discuss in these lectures a little bit of what we can now say using string theory about its behavior. So that's one of the motivations for what I'm going to do here. The second has to do with beyond the standard model physics at the electroweak scale. And of course there we all believe that the standard model is some sort of effective theory that will be superseded by something else. Hopefully we will know something about the something else in a couple of years. And the natural question for string theory is whether it gives any kind of, well, certainly not predictions, but at least natural scenarios on some level for what kind of physics we can expect. And in particular, if it turns out experimentally that the world is supersymmetric at the energy of 1 TeV, you can ask the question whether string theory gives any good models of supersymmetry breaking. And so I will hopefully have enough time to talk also about some constructions in string theory that give rise to supersymmetric Yang-Mills theories that break supersymmetry and can be used to describe the real world, perhaps. And so what I'm going to do in terms of the plan for these lectures is have two parts having to do with these two issues. The first part will have to do with gravitational duals of confining gauge theories. And here, my main purposes are, first of all, to explain what is meant by duals in this context, which is a source of a lot of confusion in the literature. And the second thing is to discuss some probes of confinement that one can discuss in these gravitational duals. I have in mind Wilson lines, finite temperature phase transitions, and the behavior of something called entanglement entropy in these theories. And the second part of these lectures, towards the end, is going to be some constructions of n=1 supersymmetric QCD from Branes. And there, the main issues are going to be to understand the vacuum structure of supersymmetric states and also discuss certain metastable supersymmetry breaking states that appear in this in these constructions. So that's what I'm planning to do, and let me start doing it. So in this first part, what I chose to do is the following. I will discuss a particular confining gravitational background and demonstrate all the issues that I want to discuss using it. But all the other gravitational backgrounds that have been discussed in the literature, such as the most famous of them, which is the Klebanov-Strassler background, have exactly the same issues associated with them. And this one is just technically simpler. So I will feel less bad when I say it can be shown that something is true. The exercises are simpler. And so let me introduce this gravitational model that I'm going to study, and then we'll discuss it. So what we would like to do is to embed 3+1 dimensional Yang-Mills into string theory. And this particular construction is due to Witten from 1998, and there are lots of subsequent papers that I will rely on that deal with different aspects of this theory. It's actually very simple to describe it because it initially just involves d-branes in flat space. And this construction starts with introducing into 10 or 9+1 dimensional space-time NC d4 branes. So these are these 4+1 dimensional supersymmetric d-branes in string theory, and let's say that they're stretched in the directions 0, 1, 2, 3, and 4. And we're going to study the low energy theory of these objects. So let me remind you of a few properties of these d-branes that I think you heard about already, even here this week. So one important property of these objects is that they preserve 16 supercharges out of the 32 supercharges of type 2A string theory in which they live. The second important property is that the massless fields on them are NC by NC matrices, which have to do with strings, each of whose ends can lie on these different d-branes. And they are split into the bosons, which are a gauge field in 4+1 dimensions. And we also have 5 scalars, which I will denote by phi I. So all these things are NC by NC matrices, and these scalars can be thought of as just parameterizing fluctuations of the d-branes in the direction transverse to the branes. And of course, there are also fermions, which have, as usual, 2 indices. So they're 4 4-dimensional spinors of spin 4-1. So these are 16 sort of fermion fields. And the low energy Lagrangian of these things is I think, again, something that you've seen, probably. So the gauge coupling, G5, and then we have the trace of the field strength squared, and then the kinetic terms of the scalars. There's a quartic potential. And then there are some fermion terms that will not matter for reasons that will become clear soon. This Lagrangian actually is best thought of as just obtained from 9+1 dimensions, where you just write a pure n=1 gauge theory Lagrangian upon reduction to 4+1 dimensions. And the gauge coupling is given by some formula like this. So it goes like G string, and it has units of length. So this thing has units of length, and that's precisely the right behavior for a gauge coupling in 4+1 dimensions. Now, actually, one thing that's going to be important for our discussion is that the relevant length for the dynamics, so the length that is actually relevant for the dynamics, again, in ways that I will make a little bit more precise in a moment, is not this length g5 squared, but it's actually lambda, which is the 't Hooft length, which I defined here. Like this. So this is a larger length. Certainly it's larger in the limit nc goes to infinity that actually governs the behavior of correlation functions and things like this in this theory. Now, what we're going to do is to consider this theory in the limit following those remarks, nc going to infinity and g string going to 0, with g string nc fixed. And we will actually take it not just fixed, but we will take it to be very large compared to 1. So g string nc is much, much larger than 1. And what this will allow us to do is to not worry about string scale phenomena, because, as I said, the relevant length is going to be the 't Hooft length, and in this limit, it's going to be much, much larger than string scale. So we will just not worry about the string scale ever again. So if there are any questions about it so far. All right. Now, for plus one dimensional gauge theory, that Lagrangian there actually does not describe a meaningful theory. 4 plus 1 dimensional gauge theory, as you probably know, is non-renormalizable. And what it means in practice is that it is essentially free at energies that are much smaller than the inverse of this lambda scale. So at energies that are much, much smaller than 1 over lambda, it's free. And at energies that are larger or a further 1 over lambda, it's ill-defined. In other words, it requires an ultraviolet completion of some sort. The Lagrangian does not define a well-defined set of correlation functions. And in fact, string theory, which is what we are embedding this theory in, will provide us such an ultraviolet completion. As you can imagine, the theory of these D4 branes in string theory is well-defined. It's not something that's ambiguous. And we will actually use this completion later. Now, this theory is very interesting, but it looks very different from what we set out to achieve, which is embedding 3 plus 1 dimensional Yang-Mills into string theory. This theory has a multitude of problems for our purpose. It lives in the wrong dimension. It has too many fields. It has all these scalars and fermions that we don't want. And also, it's highly supersymmetric. And we somehow want to get rid of all these bad properties. And there is actually a very well-known way of doing that, which is what Witten actually analyzed. In order to deal with all these problems, what we can do is compactify one of the directions that these branes are stretched in. For example, the last one on a circle. And in order, so this will solve the first problem, but in order to deal with the other two, we will take the fermions to be antiperiodic around the circle. So these 16 component fermions that I was talking about before will be taken to satisfy the boundary conditions with a minus sign when you go around the circle. And this will certainly solve this problem, because if the scalars and the fermions satisfy different boundary conditions, we are definitely breaking supersymmetry. And it will partially solve this one, because what this does, just using the usual Kaluza-Klein logic, is give a mass of the order of 1 over R4 to these fermions. And that's actually, this 1 over R4 is a useful mass scale to remember, because when things get a little more confusing in a little while, it's something to hold on to. We expect in this theory to see Kaluza-Klein states at this energy scale, the scale 1 over R4. Now, so what happens after we do this? Well, the other thing that this compactification does, which is also going to be important for us soon, here, is it introduces a dimensionless parameter into the theory where one did not exist before. So in 4 + 1 dimensions, all this theory had was this scale I mentioned, which was lambda. And in a large NC limit, that was all there was. But also, after compactification, in addition to the things I mentioned, we now have a dimensionless parameter. And that dimensionless parameter, which is going to play an important role for us later, is simply the ratio of the 5-dimensional gauge coupling and the compactification scale. So this is also something to keep in mind. I mean, I will come back to this remaining little problem here in a second. But it's important to keep this in mind. And you can think of this lambda 4 as simply the strength of the gauge coupling at the scale R4. So, so that's a dimensionless parameter that we need to keep track of. And we will actually think about what happens to this theory, and in particular to these issues, as we vary this parameter. Now, one thing that's useful to note is that when this parameter is very small, this theory reduces in the infrared to pure Yang-Mills. So actually, in this limit, where the coupling lambda 4 at the scale R4 is very small, this system achieves what we set out to achieve, which is to embed pure Yang-Mills theory into string theory. Why is that? Well, one way to think about this is that we can assume, and we will justify it in a moment, that the relevant dynamics that we're interested in is at energies that are much, much smaller than 1 over R4, or even any power of this lambda 4 times the basic Kaluza-Klein scale, 1 over R4. So let's just start with this assumption, and we will justify it in a moment. So, well, what is the dynamics at those energy scales? Well, as I mentioned, the fermions are no longer there because they have masses of order 1 over R4, and they go away. So if you just take that Lagrangian up there and reduce it on a circle, and remember to integrate over x4, which gives a factor of R4 out there, you get an action that includes gauge fields in 3 + 1 dimensions and some scalars. And it looks something like this. So there is actually now one more scalar field after the reduction, which corresponds to the 4 component of the gauge field in addition to these ones. But very naively, you would say that after the fermions disappear from this game, this is what the Lagrangian looks like. So the coupling in this Lagrangian is precisely, the 't Hooft coupling is lambda 4. So in fact, this lambda 4 has also the interpretation in the low energy theory as the 't Hooft coupling in 4 dimensions, again at the scale R4, but we still seem to have the scalars, which was, of course, why originally I said that this problem has not been completely solved yet. But in fact, there's a very standard fact about this theory that is well known just in weakly coupled field theory, which is that if you start calculating loops with this Lagrangian, the scalars, which to leading order or classically are massless, will develop a mass and decouple at sufficiently low energies. I don't want to do this calculation because we're headed in a different direction, but I do want to say that the scalars get a mass proportional to some power of lambda 4 divided by R4 and some low power. And it doesn't really matter for us what that power is because, as I said, I'm assuming that the energy that we're interested in is much smaller than any power of lambda 4 times 1 over R4. Yes, Arkady? No. So we already reduced to where, okay, let me, I probably went a little bit too fast here. So we started with the 5-dimensional theory, gauge theory, and we reduced it on a circle, and we got a theory which is 3 plus 1 dimensional, and is, if you wish, has a UV cutoff, which is 1 over R4, right? Because at the scale 1 over R4, the theory becomes 5-dimensional again. And at that scale, it's very weakly coupled. Lambda 4 is very, very small. So now we can forget about where all of this came from, and we can ask the question, in this 3 plus 1 dimensional theory, with the cutoff 1 over R4, what happens to the scalars where you compute loops with this action, which you can do because of weak coupling, in 4 dimensions. And what you will see is that, as I wrote here, those loops of 3 plus 1 dimensional gauge theory will give the scalars a mass like this, which of course is consistent because this mass is much, much smaller than the UV cutoff. And therefore, the calculation in 3 plus 1 dimensional field theory is reliable. You don't have to worry about 4 plus 1 dimensional fields, these Kaluza-Klein modes I was just mentioning, contributing. So the bottom line of all of this, and again, these lectures, for a reason that you will understand in a moment, are headed in a different direction. The bottom line is that we can just erase these scalars from the board, and at energies that are much, much smaller than whatever you get here from these low loop effects. In gauge theory, what you get is really pure Yang-Mills theory with the gauge coupling lambda 4, or 't Hooft coupling lambda 4, and this UV cutoff. Now, exactly.
So isn't there a factor of LS over R4, the scale of...
So let's see. So
the factorization scale coming into that.
So lambda 4 is equal, according to that formula, to G string and C LS over R4. So what I was saying, even before I introduced the compactification, I was saying that I'm thinking of G string and C as large and fixed, so that every distance scale that will ever appear in this problem, and that includes R4, is much, much larger than L string. I mean, in the regime I'm working in at the moment, which is lambda 4 much, much smaller than 1, there's not much of an issue, right? Because if this is distances, here is L string. So the next scale after it is this lambda, and R4 is much, much larger than that, right? So, you know, over here I might get worried about whether I'm entitled to use all sorts of low energy effective actions, but in the regime in which R4 is much, much larger than lambda, which is the regime in which I'm working at the moment, I definitely can stay away from it. We will soon discuss another regime where this issue might arise again, but here you certainly should have this kind of picture in mind. Of course, this is only the case if G string times the number of branes is very large. And I guess I should also have emphasized that we're assuming that G string is very small, so we don't have to worry about other complications, basically quantum Planckian effects.
So the scale is mass because they're essentially not reflective branes.
Right, exactly. That's the usual. But again, I mean, I wanted to stress that there is nothing mysterious here because very early on, the problem just reduces to 1 in 3+1 dimensional field theory that you have done before already many years ago, so you know what it gives. And what it gives is this. So the mass of the scalars goes like such a thing. Now, of course, we are still using these assumptions, this assumption here, but we actually landed on our feet because this theory, again, this is this hard theory. This is pure Young-Mills, which we can't solve. But the one thing that we know about pure Young-Mills is that it generates a scale dynamically, this mass gap that, for example, was mentioned in Larry Yaffe's talk. And that scale in the variables that we're using right now is equal to 1 over R4, which is the UV cutoff, times e to the minus 1 over lambda 4. I mean, there's some number here which I am not worried about. And so you see that the picture is that in this deep brain physics is that at the scale, if you plotted energies here, at the scale 1 over R4, the theory becomes 5-dimensional. Somewhere over here, the mass of the scalars sits. That's where you lose the scalars. And lambda QCD is way lower than that because it goes like e to the minus 1 over lambda 4. It goes to 0 faster than any exponential of lambda 4. And therefore, there is a very wide regime of energies where this assumption here is justified. The dynamics is described in the infrared just by the pure Young-Mills Lagrangian, and that's all there is to it. Now, of course, that's on one level good news, but on another level it's very bad news because this Lagrangian is precisely the problem that we would like to address, and what I just finished explaining to you is that embedding this problem in string theory in this limit does not buy you anything, because the problem that you have to solve is that problem that you started with, and for this you don't need all these fancy string theorists. So that's the bad news, but the reason that the lecture does not stop here is that unlike the actual pure Young-Mills theory, where you just write this Lagrangian and try to deal with it, here we got it from a bigger problem. We got this Lagrangian from this problem of D4 branes in string theory, and in this bigger problem we have more levers to put. You know, people when they started dealing with this Lagrangian very quickly understood that the main problem with it is that there's just nothing to tune. There's no coupling. There's one scale, lambda QCD. The physics is strongly coupled at that scale, and that's the end of it. So you have to solve a very difficult problem with no parameters to tune. But we do have now a parameter to tune, because we got this problem in a larger setup where the Young-Mills is the description for small lambda 4. And we can ask what happens in other regimes of parameter space, where we vary lambda 4. it could be that somewhere else we will be more lucky. Maybe there's another region in the parameter space of these brane configurations where we will be able to do better. And indeed, this is the case, and the region in which we can do better is the region where instead of being very small, this 't Hooft coupling lambda 4 is very large. So let's now consider the region in which lambda 4 is very, very large. So what that means in terms of this picture with the length scales that I drew here before is that it's actually the other way around. Right? Lambda 4, very, very large, means that actually the Kaluza-Klein scale R4 is over here. I still assume that it's much larger than the string scale, so I don't have to worry about some even more complicated things. And then the five-dimensional 't Hooft scale is bigger than that, right? This is lambda over R4, and we're now in the regime where it's much larger than 1. So lambda, the scale at which the theory becomes five-dimensional, is much larger than the Kaluza-Klein scale. And as it will turn out, in this region, we are sort of more lucky. Just like in the ADS-CFT correspondence that you've been hearing about, we're more lucky when the 't Hooft coupling of the n equal 4 super Yang-Mills theory is very large relative to 1. So what Witten proposed to do in this regime is to do the same thing that Maldasenna proposed to do for large couplings in for D3 branes. So in this regime, we can replace the D4 branes by their geometry. And again, the same justifications that are usually given for D3 branes apply here as well, so I will not repeat them. And let me just write the relevant background. So, well, first of all, what is the relevant background? Remember, we have the, well, let me comment on it as I write it. So we have the 3+1 directions that we're not compactifying. So them we can presumably just read off the geometry of D4 branes that was worked out many years ago, just in flat space, and it turns out that that's what they give. The x4 coordinate is more interesting, right? So normally we would just have here a dx4 squared if the x4 direction was not compactified. But it is compactified here, and moreover, it's compactified with twisted boundary conditions, with anti-periodic boundary conditions for the fermions. And so you have to use here a kind of Euclidean Schwarzschild solution, which showed up in the previous lecture in the context of finite temperature. And it actually will return in that guise here as well. So there is some function f of u here that I will specify in a moment. And then there is the rest of it, which, again, you can just read off the metric, the Schwarzschild metric, in this curved space, having to do with the 4 spheres in the 5, 6, 7, 8, 9 direction. So this is the metric of a unit S4, which corresponds to the spheres at fixed radial position transverse to the D4 branes. And then there's also a dilaton, which is important for what we will discuss And there's a Ramond field, which is not that important for what I will discuss. So I just dropped it here. And there are some quantities that are not defined on the board. So in units where the string length squared is equal to 1, let me define these quantities. So this r cubed, this r that appears here, is related to the 't Hooft coupling in 5 dimensions in this way. That's the analog of the relation between the ADS radius and the 't Hooft coupling for D3 branes. This function f of u, which has to do with the Schwarzschild solution, looks something like this. And of course, just like for the black hole, the critical value of the radial coordinate u is just related to the radius in a way that we'll write in a moment. So let's see. So this ukk is equal to 1 minus, sorry, I'm not copying from the right place. It's 4 pi divided by 9 lambda over r4 squared. So again, just like in Larry's talk before, there is a cigar. This is the u coordinate, the u direction. This is the x4 direction. And this is this ukk, the place where space ends. And it changes, it goes up and down as you tune lambda or r4, if you wish. Any questions about this? Okay, now, so one comment that is important here is that one can show, again, I'm not going to do this here, that the curvature of this solution is small. So all the curvature invariants are small in the region that we're discussing. So if you wish, from the point of view of this geometry of the D4 branes, this condition that I motivated before just by going sort of in the opposite direction to weak coupling is forced on you just by the fact that if this is not the case, then you can't trust the Einstein equations, which were used to derive this.
What about the dilaton? Is that also small everywhere?
Yeah, so the dilaton, as you see from here, has the following properties. So G string you should think of as just the asymptotic value of the dilaton very far from the branes in the full solution. So remember, we started with D4 branes in some asymptotically flat space, and what is called G string here is the value of the string coupling asymptotically far from the branes. So it we can take to be as small as we want. In fact, that's the G string that figures in equations like this here. Now, the actual dilaton, as you see from here, depends on position, and it goes to 0 as u goes to 0, so that's okay. And in the opposite direction, it seems to blow up, which is not okay, but it takes it a long time to do that, because if you ask what is the condition that e to the phi is much, much smaller than 1, then this condition is that G string times u over r to the 3/2 is much, much smaller than 1. And so this leads to a upper bound on u, but that upper bound is of order 1 over G string, which is of the order of NC. And so in the large NC limit that we're taking, the value of u at which this happens is very large. And there's actually a very simple interpretation for the source of this. The source of this, so first of all, it's not a problem in the sense that there is a very wide regime of radial distances here in which you don't have to worry about it, where the cigar picture is valid. But where it breaks down, it's clear why it breaks down. The reason it breaks down is that these d4 branes, after all, what is strong coupling in type 2A string theory? It means that we're going back to 11 dimensions, to M theory. And these d4 branes go back to their true nature as M5 branes wrapped around a circle, a different circle than the one that we're discussing here, the M theory circle. And so the place at which this inequality breaks down is the place at which you have to replace this geometry by basically ADS7 crosses 4, and the theory that is being discussed here by just some 6-dimensional 2-0 theory. So this is not an attitude that I'm going to take here, but you can think of this whole story, that was one of Witten's points in that paper, as the statement that pure Yang-Mills is equivalent to this 2-0 superconformal field theory in 5+1 dimensions, reduced on 2 circles, on one of them with ordinary boundary conditions, and on the other one with anti-periodic ones in a certain limit, which I discussed here. But that point of view is not going to be important for us. The important thing is that there is a very wide regime of energies, or if you wish, of values of R4, for which all of this is reliable and we don't have to worry about it. Okay, so this is the background that can be used to study the dynamics of these branes in this regime in parameter space. And what I'd like to do next, as I said in the beginning, is mention a few probes of this background that show you that we're dealing here with a confining background. Actually, David, when should I stop? Just for my...
Like 5 past, 10 past.
Fine. 5 past? Okay, so I'd like to discuss, as I mentioned, 3 probes of this gravity in this geometry that show us that we're dealing with a confining background. So the first probe of the geometry that shows us that we're dealing with a confining background is the energy of a quark and an anti-quark separated by a large distance. What in the gauge theory limit would be a Wilson line. So probes of confinement. So let me call this informally Wilson line, although we are going to do a calculation, or at least talk about a calculation in gravity here. So how would we, well, what we would like to do is calculate, put a quark at some position x in space, an anti-quark at a position y, and these are static quarks, very heavy. We're not worrying about their dynamics. And we want to calculate the energy as a function of x and y of this configuration, and we want to show that it's proportional to the separation of the quarks to x minus y. This is what we would like to do. Now, how do we do it? Well, first question is, how would we even introduce these quarks into here? And that's not that difficult. So here are the NC d4 branes that I was talking about before. So imagine that we have one more of those d4 branes, and it's very far from the other NC. Now, we are parameterizing the space transverse to the d4 branes in spherical coordinates here. So I can just think about this direction, the radial direction away from the d4 branes, as the u direction. And we have this other d4 brane that's very, very far from these NC, whose geometry we just wrote there. Now we have to introduce these quarks. the quark and the anti-quark, and these just correspond to fundamental strings because remember, this was one of the first things I said today, right? That the various matter fields just correspond to fundamental strings stretched between the d4 branes. So a fundamental string like this that is stretched between these NC d4 branes and the extra one just corresponds to some very massive fermion or boson, one of those that transforms in the fundamental representation of the SUNC. And we can just put them at two different locations, right? So this is the system of a quark and an anti-quark, and we can calculate its energy. And at first sight, it looks like there's no way we will get what we want, because clearly the energy of this configuration has nothing to do with the distance between those two. We can sort of move these fundamental strings separately anywhere we want. They just don't know about each other. And if this was the end of the story, then we would say that this background does not confine quarks. But in fact, it's a little bit too naive, because what happens, in fact, is that you need to calculate the minimum energy configuration for these fundamental strings. It could be that what the fundamental strings really want to do is something different in order to minimize their energy. It could be that it's energetically favorable for them to reconnect like that and form a sort of U-shape like that with some finite minimum value of U, which is strictly larger than this here, than the tip of the cigar. So this is just a dynamical calculation of the sort that was described here earlier. So we just need to do this. And technically, what we need to do is look at a string worldsheet where U is a function of X, basically this coordinate along which the quark and the anti-quark are separated. And we have to calculate the Nambu-Goto action and see what it gives. Now, so we need to calculate or minimize the Nambu-Goto action subject to the constraint that this U of X going to, well, maybe introduce some better notation here. So suppose the quark and the anti-quark at some positions minus L over 2 and L over 2. So we need to solve the equations of motion of the Nambu-Goto action subject to this constraint. And actually, it's not very difficult to do, but you don't even need to do this because we're only interested in this in the limit L going to infinity, right? Because this behavior is only of interest to us at very large separation. And in the limit L going to infinity, it's clear what this string will want to do. Because of the form of the metric, what it will want to do is go down as close as possible to the end of space, because there its tension is smallest, stay there for as long as it can, and then go back up because you're forcing it to. So the energy of the string, even without solving the exact equations in this limit, will go like a tension times this length L, where the tension is just given by the value of the string tension at the bottom of this well here. In other words, it will be the actual fundamental string tension renormalized by the square root of GTT times GXX evaluated at the tip of the cigar. So that's sort of intuitively clear, and if you don't believe me, you can just plug into the Nambu-Goto action these values for the background fields, and in the limit L goes to infinity, you will see that this is what the energy does. So what is this? Well, so this is equal, if you plug in all the factors, to 1 over 2 pi alpha prime times ukk divided by r to the 3/2. And we can also write it using all these formulae here in terms of the fundamental parameters, these ones, in terms of the 't Hooft coupling in 5 dimensions. And I guess there's some 27 pi squared, and then r4 cubed. So this way, this tension is written as a combination of the parameters that appeared in the specification of the problem, the 't Hooft coupling for the Branes and the compactification radius. So actually, so this is in position space. Let me draw it the inverse of this in energy, just to get a sense of what this formula here means. So of course, the square root of this T confinement is an energy scale, and that energy scale is of the order of square root of lambda over r4 cubed. But let's see where it actually lies. So in this regime here, the lowest energy in town is 1 over lambda, right? That's the scale above which the theory becomes 5-dimensional. The next scale we see is 1 over r4, which is higher. So at the Kaluza-Klein scale is, I think, what I alluded to before. The theory is already 5-dimensional here. This is one way of saying that it's definitely not QCD, or Yang-Mills theory. And I claim that this scale is even larger. So the square root of this T confinement is larger. So for example, you can write it as 1 over r4 times the square root of lambda over r4. And this is a large number here, a large dimensionless number. So the confining, the confinement energy, the one that figures in this equation as the energy of a quark and an anti-quark, is actually the largest of these 3 energy scales that are relevant in this problem. And in fact, one can even say a little bit more than this. This energy scale governs something else other than this particular observable, which is the energy of a quark and an anti-quark separated by a large distance. If you ask, what do actual fundamental strings do in this background? After all, this is, as I mentioned here, a weakly coupled background of string theory. It's basically like flat space in the sense that curvature invariants are very small. So you can just quantize strings in this space, and you can look for the spectrum of oscillator states, the kind of thing that we do in string theory in flat space. And you can convince yourself that what strings, sort of short strings, want to do is also go to the bottom here. And this is where you get Regge trajectories from. So Regge trajectories in this problem, these pictures I was drawing for you before that are familiar from just experiments in the real world, in this case come with the natural scale, which is the square root of this T confinement, because the oscillator states, at least the lowest ones of them, happen to live in that region, which is not very surprising because remember that in the regime that we're talking about here, this cigar is very, very large and smooth. So over here, it really just looks like an enormous, almost flat space. And so you can just quantize strings living there, and there are lots of them that you meet before you ever get to notice that the background is not flat. So this is another sense in which this energy scale is important. This is the energy scale of Regge trajectories in this model. Now, well, is this all there is? If you ask, well, what is the spectrum? What is the actual spectrum of states that you would encounter if you quantize strings in this model? So as I just said, the spectrum of states in string theory in this model certainly will include sort of the kind of oscillator states with separations of the order of this T confinement. But also, if you expand just the supergravity action, you get states with energies of order 1 over R4, which, as I just mentioned here, is much, much lower. So in the supergravity, it's a calculation, a complicated one that I'm not really going to review here. But it shouldn't be very shocking to you, because as I emphasized in the beginning of this lecture, the system we're discussing is nothing but just D4 branes on a circle of radius R4. So in a sense, these are just the original Kaluza-Klein states of all those fields that we were not thinking about upon reduction to 3+1 dimensions. All those fermions and scalars, it's clear physically that this is the scale at which they should appear, and the way they appear is this way, by expanding the supergravity action and looking at the spectrum of small fluctuations. And these are actually the lowest lying excitations in this regime. So these, here we find the string states, oscillator states, and over here we find Kaluza-Klein states. Now, so you see now in what is the sense in which gravity, and this is actually one of the most important points of today's lecture, so it's a good time to wake up. Yes, excuse me.
Since it's the main point, I better let you make
Yes.
it first, yes.
So the main point of this lecture is this. I mentioned at the beginning that I'm going to explain to you in what sense the gravitational confining model that I'm going to discuss is dual to pure Yang-Mills theory. And I just finished explaining to you that. And so on some sort of very low level, technical level, these two models are related by tuning the continuous parameter that I called here lambda 4 from very small values to very large ones. And in one limit of this parameter space, in this one, the theory reduces to pure Yang-Mills in the sense that I hope I made precise here. And in the opposite limit, it can be analyzed using these gravity techniques. But if you think about it more physically, it's really this picture that you should be thinking about. Because, as I said, QCD was so hard because there were no parameters, no tunable parameters. Now, in field theory, tunable parameters is basically synonymous to hierarchies of scales. And what we managed to do in this string example is to embed the field theory problem into a larger setup in which we can generate such a hierarchy of scales. After all, in pure Young-Mills theory, there is no story like this. There is no one scale at which there is one type of states, Kaluza-Klein states, and another scale at which the Regge trajectories start. Everything lives around the scale lambda QCD, and that's the end of it. Like if you look at these plots that people put the resonances on, you just don't see such a separation of scales. The gravity region is one in which you manage to generate such a separation of scales, which of course is not a feature of QCD. And this is something that is shared by essentially every other example of gauge gravity duality that you've probably ever seen. So for people who are familiar with, say, the Klebanov-Strassler solution, there is some parameter in the gravity solution, which they call G string times M. And when that parameter is small, it's gauge theory, but then there isn't any kind of separation of this sort, and you cannot trust gravity. And in the opposite regime, which is the regime in which they actually write all their metrics, there is such a separation again between Kaluza-Klein states of the supergravity and string states that live near the tip of a much more complicated looking cigar, where these functions that enter the geometry can't even be written in closed form. It's incidentally also the case in ADS5 crosses 5, of course, because there are the sort of Van Nieuwenhuizen type states, which are like Kaluza-Klein states, and then there are string states that start much higher. So I will return to this after I mention the other probes of confinement here, but you wanted to say something?
Well, it's just that you said early on that we would never have to discuss oscillator states.
Right, right.
Just going into low energy
Right.
regime. Now you're putting up oscillator states.
Well,
So the question was, what's the relationship between those and the original state?
well, yeah. So
Forget about it.
to be more precise, what I said in the beginning of the lecture is that I do not want to think about physics at the scale M string ever again. And if I try to put the scale M string on this plot, it would go here somewhere. Okay, so the string scale, which is the scale at which the oscillator states of the original D4 branes in flat space start showing up, is still much larger than all these scales. Notice that that's one of the reasons why I wrote, where was this? Well, I guess this formula here. So notice that the tension of these confining strings only depends on the two length scale, right? So the tension is an object with units of energy squared. I wrote it here as a distance divided by distance cubed. And both distances that appear in this ratio are distances that have nothing to do with string theory, right? I defined them in the beginning of this lecture using just the low energy gauge theory, the 't Hooft coupling in 4+1 dimensions, and the radius of the circle on which I compactify my strings. The original alpha prime, or M string, indeed does not enter into this formula, which is, by the way, it's exactly what you do when you replace D3 branes by ADS5 crosses 5, right? Because the strings, sort of oscillator states on ADS5 crosses 5 don't have anything to do with oscillator states that lived on the original D3 branes, right? If you take n D3 branes, then in addition to the n equal 4 Young-Mills that lives on them at low energies, there's also a tower of oscillator states with energies like M string, 2M string, etc., that lives on them as well. And those things are gone forever once you pass to ADS5 crosses 5, right? All the states in string theory in ADS5 crosses 5, including the string states, describe just the n equal 4 super Young-Mills states. And the same is true here. Here we already got rid of all these guys, and we're now focusing on sort of what you can think of as the low energy theory.
Doesn't that make it though rather remarkable that you threw away everything to do with the string? You still end up with something that looks like a string.
Well,
I mean, well, in fact, the way you did the calculation makes it seem that it makes it clear that somehow you do have, well, I mean, there's the question of there's a lack of explanation of why you end up with string, well, something that looks like string physics, given that you've apparently thrown the string physics away.
right. So this is, but I think that what I was trying to point out is that, well, yes, it's remarkable, but the Maldacena conjecture in general is remarkable. And the Maldacena conjecture replaces n equal 4 super Young Mills, which is a field theory, specifically with string theory on ADS 5 crosses 5, not, say, loop quantum gravity on ADS 5 crosses 5. Okay, and and indeed, because it replaces it with string theory on ADS 5 crosses 5, strings will show up in the problem. So all these things are sort of, I mean, I would say it's the level of remarkableness is the same in all the examples. And indeed, it's a very powerful tool, but the thing I was trying to emphasize here is what kind of information it provides you. It provides you with information about this system, but in a regime which is different from the one you want it to be in. But it's nice that qualitative things like this formula still work. So that was the first of our three observables that are probes of confinement, and what we found is that it's okay, that this gravitational background indeed has the property that the energy of a quark and an antiquark that are separated by this distance L grows linearly with L, and we even were able to calculate the tension of the confining string, point out that there are Regge trajectories at that scale, and I guess it's a good time to stop because, as I mentioned, what I have to do next is discuss the other two observables, which are the finite temperature phase transition and the transition in the entanglement entropy, which are two more observables of this sort that show you that this geometry is qualitatively okay. So I think I'll stop here. So what's the plan?
Questions? Comments? Right, I have a question.
Yes.
I suppose we can't be sure there's no phase transition as we vary now.
Yeah,
Otherwise, you pick up the clay millennium.
Probably win $1 million. That's you three.
yeah, I guess, well, so this is a general comment that one can make about these dualities, that there is always the issue whether the things that you're computing in one regime are separated by a phase transition from another. So I guess I'll think whether I have something better than what I'm about to say by next time, but in a sense, those observables that I'm going to tell you about provide evidence that this is not the case, in the sense that, at least in those three ways of probing the theory, the gravitational background is in the same phase as the weakly coupled pure Yang-Mills theory. But if I have something better to say, I'll tell you next time.
Any other comments? David.
I'm trying to understand, when you reduced, through getting rid of the fermions by antiperiodic, down to the scalars plus Yang-Mills, and then the scalars acquired a mass through loop corrections. Right. Is this effectively like Coleman-Weinberg?
Yeah.
And so, do you know always switch the sign of that? In other words, are you going to be in the which phase of the Yang-Mills will you be in? Do you always
yeah. So well, Coleman-Weinberg, of course, is often done without gauge fields, right? Where you just have, say, scalar fields, and you calculate an effective potential for some fields after integrating out others. And the details depend on whether the loops you're dealing with involve gauge fields or scalars or fermions. In this particular case of Young-Mills fields coupled to scalars, I believe the answer is that you get a positive mass squared, and the scalars are just stuck at the minimum with the kind of mass that I wrote there, which goes like some power of lambda 4 times the UV cutoff. So it's okay, in other words. You don't end up in the other.
I thought the original Coleman Weinberg, so I'm going back a long time.
Yeah.
That it was a billion Yang-Mills plus charged scalars, and it produced the negative. So it's
Right, but I think here, so you ask what is the difference? I mean, I would have to look. I don't remember the details by heart, but I believe for non-abelian, so if you have well, of course, it's a very different example, right? Because you're talking about U1 gauge fields with scalars in the fundamental, and this here is SUN gauge fields with scalars in the adjoint. So what I'm trying to say is that I believe that, well, let me put it this way, it better be for Witten story to work that this exercise where the scalars are in the adjoint gives this answer.
But in the setup you described, the previous step where you were basically integrating out your
Fermions.
your fermions as well as the higher dimensional,
Oh, the Kaluta-Klein modes of
decay
everything
modes.
else, yeah.
right? They also contribute to the effective mass
Right.
for the scalar. And because you chose your twisted boundary conditions for the fermions,
So
it
you're
works
saying
out
that
the same way it does in the thermal case. That it
you're
works-
saying that it could be that it comes from the Kaluta-Klein modes of the fermions and gauge fields and all of that as well.
yes.
Yeah, I actually, it's been a while since, I mean, I did look at this calculation. I don't remember the details. So I think you're saying that it could be that this problem would give a negative mass squared, and it would receive a extra positive contribution from the Kaluta-Klein mode, such that the total is positive or something like that.
Yeah, I'm not even sure whether the four-dimensional fluctuations give positive or negative. I'm just, I
Yeah.
don't
No,
know.
I mean, I completely agree that
Why-
the honest exercise is, of course, to start with the full problem, with the Kaluta-Klein modes of the fermions and the scalars and the gauge fields, and just see which ones give the dominant contribution to the mass. And I believe, I mean, you know, all this is from like 9 years ago. I believe the answer is that the mass squared is positive, and I don't remember what is the dominant contribution to the mass squared.
Technically, forgive me being naive, technically if you did the really, really full calculation, would the mass actually be a finite quantity? Because there's no reason if you take the action at the bottom of your left hand,
Here.
there's no reason why that calculation will actually give you a
Yeah. So it's supposed to give what in the field theory would look like a quadratically divergent answer. But of course, I told you where to cut it off. The UV cutoff is 1 over R4, right? So the UV cutoff is the place where the field theory becomes five-dimensional. So the exercise I would do if I just had to do this would be the field theory exercise with a cutoff of the order of 1 over R4. And one of the reasons for all these wiggles was that, of course, things will depend on exactly what the cutoff is. But I think there is a well-defined calculation you can do in string theory in this direction, where everything is finite. And the answer you will get is some power of what I called lambda 4 times 1 over R4. The coefficient is finite. Divergences are not an issue. And if you wanted to translate it back to field theory language, is what I was saying before, I just don't remember. So it's clear that in the field theory language, you would have to put a UV cutoff at energies of order 1 over R4. I don't remember whether... See, one of the problems with these Kaluta-Klein modes is that they're all at energies above the cutoff. So I just don't remember. That's the honest
If
answer.
you do the calculation in 5D, then you have supersymmetry in the ultraviolet, and I think that makes the mass fine.
Yeah, that could, that is, of course, well, you're saying you don't have to go all the way to string theory, you can just deal with the five-dimensional
The non-real
gauge
life
theory
isn't
with
an issue.
16 supercharges.
I think that's
Well, then you have to, the question is, does the non-renewables ability,
no, I think you're just lucky for this particular
Yeah, you say you will get some finite. Well, I shouldn't talk about things I don't remember. Sorry. Okay, so thank you.
Okay, let's thank David again.